Evening and welcome to the ZP Developer Zone. So we like to do this webinar every week, and it's really just answering technical questions that have come in during the week. So I'm going to jump straight into it. And I know the first slide here is going to say the 10th of November, but we actually have gone live, so it is actually the 9th of November, but it's sometimes easier just to do these things on a Saturday evening as opposed to a Sunday morning. That said, let me go forward with the questions. So today we're going to talk about configurations of molecular assays. So I'll talk about blocking assays, intercalation assays, conformational change assays, and I've got one more in there as well. It's just slipped my mind for a second, but we'll talk about molecular assays this evening. I'll also talk about a particular paper from Italy. It's really about putting silver nanoparticles in zeolites and how to commercialize this kind of work. I'll also just put up a little bit of data about graphite versus graphene. I'm not this amazing fan on graphene because I don't think it's the wonder material that people kind of, in the world of biosensing, I don't think it's necessarily a wonder material. And you'll see the data tonight as well. But I think my biggest concern sometimes with graphene is at this moment it can be expensive, and it doesn't, in the world of biosensors, it's kind of extra, let's say, conductivity doesn't add a lot of value. Overall, the electrochemical cell, the highest impedance is actually through the sample itself. But I'll discuss this during this webinar. Geosmin, there seems to be a very strong interest in Geosmin at the moment. Actually, I'm going to make a comment that Geosmin is this chemical that if you're doing aqua farming, you're kind of growing salmon in recirculating aqua systems. There can be bacteria get in there, and the bacteria can give out this sort of turpentine called geosmin, and it can make the fish taste kind of an earthy taste, and people don't like it, and it spoils the salmon. So the farmers are very keen on making sure that this geosmin is actually not in high concentrations, and I think it's actually even in parts per trillion that they're trying to avoid, which actually parts per trillion was a kind of a challenge. But just of recent, you get these PFAS chemicals, these perfluoroalkylated perfluoroalkene substances, and different branch of compounds, but a similar sort of, let's say, issue that parts per trillion detection required. The molecules don't have a lot of handles on them. Their natural chemical moiety doesn't make them naturally redox active, but I think the solutions for geosmin detection and the solutions for doing this PFAS detection are actually quite similar. Anyway, I'll get into that. Silver electroplating. Somebody's trying to electroplate silver down, they're getting a rough surface. If you're getting a rough surface, you're doing silver plating, you're probably just doing it at a too high a current density. What is wrong with potentiostats? Which is kind of an ironic question coming from me because I'm sitting here in front of a potentiostat. So obviously with my super biased hat on, there's nothing wrong with potentiostats. And I think but actually some of the problems that they list out as what's wrong with potentiostats, I think we've actually overcome that at ZP when it comes to the Sensi or potentiostat. This is a real beauty of actually being able to do both fundamental research and being able to use it to actually turn research into products, sort of commercializing things, and also just having greater impact as well. So I will talk about that a little bit this evening. So what's wrong with potentiostat? Depends which potentiostat you're actually looking at. Last week we did a fairly deep dive onto Aptamers. Somebody's come back with some further questions on Aptamer, so I will answer those this evening. Also CGM. A company in Asia is looking to get into continuous glucose monitoring. I kind of basically think that their strategy is slightly going backwards, when in fact, it's always good to go forward. So I'll try and give my some thoughts on that. A group that's trying to do longitudinal study, hormonal tracking. They're trying to do cortisol, testosterone, and potassium. I know potassium is not a hormone, but I will strongly emphasize that the one that I would go forward with is potassium. At ZP, we do have a cortisol sensor, but we don't make it available, generally available, because it's quite a valuable sensor, just in intellectual property perspectives. And then on the testosterone front, we are shipping, in fact, testosterone sensors to beta users at the moment for doing it in saliva. I know that group is not particularly interested in doing it in saliva, but if anyone is, just out of curiosity, I've just scanned a QR code here. This is an amazing, obviously I'm biased, amazing device, because in fact, different QR codes. So I've got amperometry here, open circuit potentiometry here, impedance spectroscopy here, linear sweep voltammetry here, cyclic voltammetry here, square wave voltammetry. In fact, and I was having a conversation the other day, and somebody says, well, how can you do square wave voltammetry if you're using QR codes? Well, once I go continue, then all of the sort of settings pop up. So it acts like it's a sort of standard potentiostat. I think the simplest one to kind of understand, in fact, if I just do it really quick, is amperometry. Yeah, amperometry. So as soon as I go amperometry, then I can change the run time, I can change the save rates, I can change the applied voltage, I can change the current range. So it is a very elegant potentiostat. And one of the questions that I'm going to go through tonight is what's wrong with potentiostats, and actually where they criticize is the complexity of potentiostats. So in some ways, I think the Sensi All is actually returning a potentiostat to an instrument that hasn't got out of hand. When you look at many potentiostats now, they've got sometimes lineages of like 40 years old. So the software engineers in those products have just kept on adding features and features and features. And in fact, potentiostats often have multiple applications: capacitors, batteries, corrosion, and fuel cells. And then some of them are also okay for biosensors, but actually biosensors and a potentiostat that's good for batteries and good for biosensors is not the same potentiostat. They're very different instruments. So this potentiostat in particular is really tuned up for doing biosensor development, and because we've got a cloud system attached to it, I can actually process the data and turn that data into analyte concentrations as well. All right, with that said, let me go forward a little bit faster. So I will talk about hormonal longitudinal tracking, but I will say that the cortisol sensor is not something we make available unless the client is really well funded. We do have testosterone sensors, but I'm not going to be able to sort of promote that you can use those in sweat. People are welcome to buy and try, but it's not something I can support. Whereas actually I can say that potassium measurement in sweat is good, because we've got some first-hand experience of it. I'll talk about glucose microneedles. Somebody's very interested in glucose microneedles, so I will discuss that. Screen-printed electrode holder, just how to use it. Biosensor circuit. So at ZP, we do have a very small circuit. In fact, the circuits used in products like this, I'll just hold this up. So inside of here, there's actually a very functional potentiostat. This is actually a wearable microneedle watch. But A, the watch is not available on the web store. We only use it with really well-funded clients. And B, the biosensor circuit that they've got is not programmed at this moment to be a potentiostat. But I'll discuss that. And then lastly, glucose in urine. Somebody wants to do glucose measurement in urine. They want to have 85% accuracy, so I will discuss that this evening. Now, the reason I list these questions out initially is so that you don't have to sit here and listen to me go through 13 questions. This could be well over an hour, so hopefully you can jump through, find your question, and save yourself some time, because I've said it, but the most valuable asset you've got is your time, so that's why I've listed these questions out here. If you are interested in making point-of-care diagnostics, there's two sort of form factors that we get quite heavily involved with at ZP. Point-of-care diagnostics, so I would describe this as a kind of point-of-care diagnostic. You've got a sensor, you've got a potentiostat. In this particular case, we can drive this system using an app. So if I want to do something like impedance spectroscopy, for example, I can scan the impedance spectroscopy. I've got all my settings available to me. So I would describe as a very point-of-care application. We also have another sort of form factor, which would be something like wearable sensors. So these would be the sensors. This would be the watch. The kind of archetypal biosensor on the market at the moment. I'm just going to pull one out. And this is not my product. I'll just be very clear about that. will be some of these kind of glucose sensors. This is an Abbott product. Now, the reason I bring that up is because we do a webinar, and I'll just go back to my actual screen. We do a webinar every month. There's one on the 25th of November, and it will be on wearable biosensors. So if you're interested, sorry, that's not wearable biosensors, that's point of care. My apologies. If you've got a choice in life about doing a point of care diagnostic or point of need assay, where you just take a sample, put it on the sensor, get a reading, dispose of the sensor. If you've got a choice between doing that and a wearable, please choose the point of care path. You'll get to market much easier, and getting to market is really important because so many people will spend so many years developing and never actually getting to market. So if you've got a choice, take the path of least resistance, and I would say go for point of care, point of need diagnostics. You can get to market, and you can mature your company into doing continuous monitoring. But that will be my kind of advice on that. With that said, if you're interested in commercialization of point of need devices, 25th of November, which is about 16 days out from now. But don't worry, if you see this, if you're watching this let's say webinar years later, the links will take you to the upcoming webinar. So don't worry about missing it. If you see any links pop up this evening, by the way, or while watching this video, I'll have to put them underneath the video as well. We are doing a wearables webinar. That's on the 12th of December, 2025. You notice that I do one in the morning and one in the afternoon. The nice thing about the company is fairly international, but I happen to live in the UK. We do one in the morning, one in the afternoon, because then that actually works really well with the different time zones. So, you know, we'd like to be inclusive, so we can cover our colleagues in Asia with the morning and cover our colleagues in the sort of USA, Canada, Central America, South America with the afternoon, for example. Something that's I'm quite passionate about is translation of academic research into tangible products. I think, in fact, in academia, people won't just now be, let's say, you know, scored. And I don't like this scoring of publications used to score people. You know, it's sort of, you know, we know it's leading to problems in academia. But one of the ways of scoring is actually evaluating impact, and impact can also be improved by, did you get that technology out of the lab, and especially did you commercialize it? So as EP, we're quite interested in the commercialization of academic research and the translation of research out of the lab. In fact, the whole raison d'etre for ZP, the whole reason this exists, is actually to translate academic research out of the lab. It's a unique type of potentiostat where we actually have, you know, QR codes. So it all drives off my smartphone. So I have QR codes on cyclovoltammetry, an old favorite. So you can do cyclovoltammetry experiments using this. But because we have every time I do an experiment, I can send the data to the cloud. We have a cloud system called Julie, and you'll see Julie in action shortly. I can process the data and actually turn it into a concentration. So watch out for that. Anyway, back to this. So on the 10th of December, we'll do a webinar more around for our colleagues who are interested in translating their research actually into products. And we're also going to have an in-person webinar on the an in-person workshop. So if you're interested in training with ZP, you know, covering the kind of fundamentals of, let's say, biosensors, but then actually doing a practical for every sort of, you know, if we discuss amperometry, we'll do a practical on amperometry. If we talk about open circuit potentiometry, we'll do a practical on open circuit potentiometry. If we talk about impedance spectroscopy, we'll do a practical on impedance spectroscopy. Same for linear sweep, cyclic, and square wave voltammetry. So we will do, I don't always call them lectures, I would just call them discussions, and then actual practicals as well. So that's a 2-day workshop. So on wearables, point of need testing, and it'll be in Norway, and it's on the 22nd and 23rd of January 2025. Again, if you're watching this some years from now, the links will still take you to the website. We'll probably have updated with our most recent workshops. So I'm going to talk about molecular assays. So I'm sort of thinking about things like sexually transmitted diseases. People are very interested in identifying those viruses. Sometimes it's not, you don't need to actually quantify those viruses. I mean, you know, I don't want to be morbid, but, you know, whether you have HIV or not, it's whether you have it or not is the critical parameter then not, what is the viral load at any one time. So that would be the kind of target that somebody who is maybe interested in a molecular assay would be kind of, the real world problem they might be solving is, does somebody have chlamydia? Does somebody have gonorrhea? Does somebody have HIV? And so I'll talk about some ways of doing electrochemical molecular assays very shortly. I'll talk about binding assays, blocking assays, intercalation assays, conformational change assays as well. When I talk about this stuff, when I talk about electrochemical molecular assays, it's not from my point of theory. This is actually something that ZP is super active in. You may be super aware, I hope you are, that at ZP we manufacture really good screen printed electrodes. Now the biggest users of our screen printed electrodes is actually ZP. So people will actually come to us and say, okay, well, I'm kind of aware of Zimmer and Peacock, and I'm aware of your products and your material online, and then they will say, will you actually develop us an assay? Now, developing assays and products for people is an expensive endeavor. So with academia, I tend to, provide the tools that say are necessary to do that, which would be the potentiostats that we use, the screen printed electrodes that we use. Webinars like this where I'm about to talk about strategies for making a molecular assay. That's how we kind of support companies that are not super well funded, or how we support academia, but we're well funded companies. We actually do the work ourselves in the labs because we are ISO 13485. Being ISO 13485 means you don't just do the work, you actually document the work properly. So later on you can submit it to the FDA or get it CE marked in Europe, etc. With that said, let me go back to the slide. So let's talk about molecular assays. So the first one I'm going to talk about is this kind of binding assay. So you've got, so let's say you've got a single strand of DNA, which I've indicated with the red here. You've immobilized it on a gold electrode. ZP has some hypervalue gold electrodes that are pretty good for this kind of work. We do it. And you have a target. It may be even a target that you've amplified using PCR, polymerase chain reaction. And you want to detect this PCR. Now I understand that traditional way of measuring PCR would be like fluorescence spectroscopy. But electrochemistry is a really good science for, if you want to get a science or an assay out of the lab and into the real world, then electrochemistry is a really good science for that. I mean, later on I'm going to be talking about glucose detection in urine later on. So this will become more, interesting when I actually talk about that. But I'm just going to change screens for a second, because what's the most common biosensor measurement made per day? And it's probably the glucose strip. Why is the glucose strip electrochemical? Why isn't it not fluorescence? Why is it not optical? I will answer that. Well, I'll answer it now. It's because it's low cost, simple to do, no shielding from ambient light. It can work in really unprocessed samples like whole blood. So wait until about one of the questions much that later down, and I'll actually do a demonstration of this. But the reason I'm saying this is because I'm now talking about how to measure the end point of a PCR reaction, for example, but I'm actually going to talk about doing it by electrochemistry. And you may say, well, I've got fluorescence spectroscopy, why would I even be bothered? If you've got samples like this, this is not a super clean sample, it's cloudy, it's got bits in it, it's got a slight orange color on it, that doesn't work well with fluorescence. But electrochemistry doesn't care about the particles, doesn't care about the color, it will still run. So electrochemistry is good for doing in-field tests, including molecular assays. Now let me go back to my screen. So I'm going to talk tonight about 4 ways of doing molecular assays using electrochemistry. So I have a gold electrode here, I have a SAM layer, self-assembled monolayer on it. I have some single strand of DNA, which is complementary to the actual target. The target is sort of brought onto the sensor, and there's a binding assay. And then we can bring in a probe. A probe is another complementary single strand of DNA, which binds to the target, and we essentially form this kind of hybridization, this trimer between the capture probe, the target probe, and the sort of signal probe. And in bringing that signal probe, if you tagged the signal probe with an electrochemical molecule like ferrocene, you can do something like linear sweep voltammetry, and you can actually pick up the fact that this binding event's taken place, and the fact the amount of binding will actually increase the signal in this particular case. Just want to change screens for a second and just kind of say, I'll move these glucose material out of the way. But if I was going to do this kind of assay, I would have taken one of our gold electrodes, functionalized it accordingly. I would have brought the target onto an electrode like this, and then I would have used... Now, in the good old days, I could have used linear sweep voltammetry. Linear sweep voltammetry is nice and simple. You can just see it from the parameters here. These days, we'd actually probably do square wave voltammetry, which is that, square wave voltammetry. With square wave voltammetry, you've got just a few more settings to think about. And I'm also quite keen on impedance spectroscopy for these kind of assays. So we also have impedance spectroscopy as well, with also got its own settings as well. So in order of, if I'm going to do an assay like this, to get a feel for it, I would use linear sweep voltammetry because it's so simple to just set up and run. To optimize it, I would then probably go into square wave voltammetry and even EIS. And I'm not really, it's experience that's sort of teaching us at ZP whether, you know, in the end, are we going to always do square wave voltammetry or EIS? At the moment, we mostly do square wave voltammetry. But you learn tricks and tips over the years. It's probably worth saying that because of the way our business runs, we do hundreds of hours of this kind of work per month. It could even get into thousands of hours. So, you know, you build up a lot of experience because of that. We're not doing it in the kind of academic sense. We're doing it because people have genuinely paid us to get them assays that work and are robust enough to actually go to market. And we're doing really well on one at the moment. So molecular assays, this is kind of the way I've shown it here, where you've got this kind of trimer immobilized for gold electrode with a reporting molecule here. This is a kind of the most complex way of, let's say, doing it. And I've mentioned you can use linear sweep voltammetry, EIS, electrochemical impedance spectroscopy, or square wave voltammetry to do this. This is a simpler assay where you would kind of take a gold electrode. Again, you may put a binding molecule onto it. Notice I put some spacer molecules in here as well. So when you're making self-assembled monolayers, you often have a kind of capture probe, but you often do want to space that capture probe out a little bit. Otherwise, there's too much steric hindrance and all these kind of capture probes will kind of crowd around each other. Then you will bind the assay, and then we will use a reporter molecule that wants to get to the surface. But the ability for that reporter molecule to diffuse, and that reporter molecule is mobile and it's electrochemically active. But when you sort of essentially block the surface through specific binding, we could potentially decrease the amount of reporter molecule that actually get to the surface. So this is quite a simple way of doing an assay. So that is something that we would do quite often. Same kind of thing, you can use linear sweep, square wave voltammetry, and EIS. Of course, you know, super biased. If people do it on our Sense It All platform and use our screen printed electrodes, then I can support them. I am supporting people who are not even on our potentiostats and not on our screen printed electrodes. I mean, that's one of the support questions I'll be doing this evening. But going forward, it is hard because one of the problems I've got, one of the guys has got this evening on this kind of work is he's really got a problem with reproducibility. Fundamentally, it's the electrodes he's using that are actually the reproducibility problem, but I'll address that later on. So blocking assays are quite straightforward. I quite like these intercalation assays. They are quite straightforward. So you have a target, you have a capture single strand, let's say, of DNA. You have the complementary DNA that you've either amplified or it's just you've lysed the sample and that DNA is there. And then you actually have a redox active dye. Lots of dyes have a property of intercalation where they can actually bind into the grooves of a double helix. Dyes are useful because they are they can intercalate and they're often electrochemically active. And in doing so, they essentially bring an electrochemical signal to that. So in binding, you get a signal, and then the amount of binding is also indicative of how much hybridization you've got going on here, and therefore how much target let's say DNA was also in the sample as well. So I quite like this assay because it's actually quite simple. The good thing about ZP, and if you're ever looking for, we don't give advice based on, a bias. So the bias is we like electrochemistry, we like wearables, we like disposable sensor systems. So there are those biases. But when we do an assay, we're always trying to keep it as simple as possible. Why? Because simple means easy translation. There's definitely a philosophy running through ZP. The philosophy running through ZP is, hi, my name is Martin, and you say, I'm interested in electrochemistry and biosensors. I say, great. Are you interested in getting to market? And if the answer is yes, that is what we're super interested in as well. You may not be interested in getting to market today, but if you're going to have a real impact with your science, it does have to leave the lab and get onto the market. So we like simplicity, not for the sake of it, but because actually it allows for commercialization and translation much quicker. So I do like intercalation assays. They are quite simple. I actually like these assays as well, conformational change assays. Now, at ZP, we do work on conformational change assays. So, you can have a sort of hairpin configuration in something like a DNA capture probe. You can put a redox active molecule on there. I'm showing this on a kind of gold electrode. So, gold electrodes are synonymous with self-assembled monolayers. And then you would kind of have a signal due to that hairpin and that redox molecule being kind of close to the surface. And then you could have a target which comes in, and then on binding, everything straightens up a little bit. And in doing so, the signal decreases. And therefore, you've got an indication of how much is the target present in the sample and how much of the target is actually in that sample. It's a harder probe to develop because you've got to kind of have that hairpin configuration that then reacts or opens up and hybridizes with the target. But it's elegant and it makes for a simple assay. So I do like it. You just have to put a bit more work into the design of that capture probe in that particular case. I've mentioned it, but we do square wave voltammetry and EIS a lot when doing these kind of assays. So I've mentioned 4 assays there. Three of them are quite simple. The first one, which was a kind of a sort of binding assay when I formed that trimer, those are the more complicated assays, and I sort of tend to steer away from them because complexity just makes it harder to make a low cost, easy to use point of care diagnostic. If somebody says to you, oh, I'm really interested in lab on a chip, that's a really big problem for me when people say lab on a chip, because lab on a chip suggests that I'm going to take the workflow that I would otherwise do it in my molecular biology lab and just translate it onto a microfluidic device. So that means wash steps and you add the reagents, you wash materials away, you add other reagents, you wash them away. So lab on a chip it sounds like an elegant idea, but it actually leads to quite complex assays. It's almost a philosophy is wrong. Somebody said to me once, it's not lab on a chip. If you want to make low cost assays, you have to shrink it, you have to rethink it. So if you're going to translate an assay onto a low cost medical diagnostic, don't just take the workflow that was otherwise used in the lab. You have to really simplify it. So 3 of those assays were simplifications, and the first one I showed was actually a more complex assay and harder to translate into, let's say, real world products. But we do use EIS quite a bit, square wave voltammetry quite a bit on this as well. You're not obliged to use ZP potentiostats and ZP screen printed electrodes, but the reason that you might be is if you're using our potentiostat, then there's actually a pathway. This potentiostat, it looks much more like a product than you would be typically used to. And actually we have a very simple way of taking assays that are developed on this and actually turning them into, and I'll do a demonstration. Will I do a demonstration now? I will definitely be doing a demonstration, so hang on. Where I actually do a test where even though I'm running voltammetry, you end up with a concentration of that sample. So it's a very elegant potentiostat, and the only potentiostat in the market that's cloud enabled. We process the data in the cloud and we send a result back to the phone, something like a concentration. So watch out for that. So you're not obliged to use our technology, but it does, of course, make it easier for us to both support and for you to actually get to market. So if you're doing molecular assays, I think this hypervalue gold electrode is good, and I think these carbon 501s are good as well, and there will be links underneath the videos as well. And we can do amperometry on this, open circuit potentiometry on this, impedance spectroscopy on this, linear sweep voltammetry on this, cycle voltammetry on this, and square wave voltammetry on this as well. It's kind of interesting actually, because people would say, oh, you know, what's your specification for the potentiostat? The thing about ZP is, if you're interested in biosensors and in molecular assays, this potentiostat will work. Why? Because we use it day in, day out for this kind of work. You know, ZP is interesting because we build tools that we actually use, and then we happen to put them on the website as well. So it's an unusual sort of business model, but it works for us, let's say. And yeah, we do also have a data pipe as well in the cloud, and hang on for a demonstration, because at some point I will do a demonstration this evening about the whole workflow as well. In fact, I might do it in a minute. So question number 2, somebody showed me this paper, said, you know, can we translate this paper into a commercial product? So let's talk about that now. Just want to, you know, I may use some of their data, so I just wanted to make sure that you understand whose data I am showing. So this is the name of the paper: electrochemical strips modified with zeolites, embedded with silver clusters for biosensing. I know I've just slightly changed the wording there, but it just feels more natural for me. And it's led by a good guy called Stefano Cinti, and I will discuss their work. So the first thing that they're doing is they are going to modify screen printed electrodes. So at ZP, you know, we're big producers of screen printed electrodes. The thing that we really focus on screen printed electrodes is actually reproducibility. So you will see me discuss that this evening as well. Reproducibility is king. Reproducibility of screen printed electrodes is what's killing and holding back a lot of academic research. Academia knows that actually the screen printed electrodes that they're either producing or they're buying are not reproducible. You'll see loads of demonstrations from ZP online, and you'll very rarely see us do a calibration in our assays. And why is that? Because we put a massive effort into making these screen printed electrodes reproducible. With that said, let's get back to the paper itself. Okay, so they're taking a zeolite, and I hope I pronounce this right. So I'm going to say forjazite X, but the J can sometimes be said as an H in some languages, so I'm not sure if this is foresight or forjazite, but forgive my pronunciation. And they're taking some silver ions. They possibly, I know the silver ions are going into the zeolite, but it may actually also be reduced to a silver cluster, so it's not Ag+, but it's Ag. And then they're not drop casting them onto ZP electrodes. I think in the paper they're actually manufacturing their own electrodes, but we do a really nice 501 carbon electrode. Really sweet reproducibility. Reproducibility is king. If you don't have, especially the way they do the work, the way they do it, I think they'll use something like square wave voltammetry. And so in square wave voltammetry, you want the area under the curve or the peak height to be proportional to the analyte. But of course, if you're not making a reproducible electrode, the area could be variable, or the roughness of that electrode could be variable, and that could also be a contributor to the signal. And that's what's often holding back the translation of academic research. So they drop cast onto the electrode. What I like about this work, it resonated with me because I'm talking about those molecular assays earlier on. I talked about a whole philosophy at ZP. Keep it simple. If you keep it simple, it can be translated into a real product. If you're doing it on glassy carbon electrodes and you've got multi-steps, you're not keeping it simple. It's going to be harder to commercialize it. But this is kind of simple, that they prepare a material, they drop cast it on the material, and then they show a couple of applications. And one of the applications they show is that they can sort of have a glucose reaction with a glucose enzyme, and they can generate hydrogen peroxide. They don't quite put the mechanism in the paper, but I'm sort of guessing what the mechanism is. But glucose reacts with its enzyme. In the presence of oxygen, produces hydrogen peroxide. I got a suspicion that the hydrogen peroxide is oxidizing the silver in the clusters. You get silver ions, and I think it's the silver ions that they're then detecting on the electrode. And I also like about this paper is I think, I hope I'm right when I say this, I don't want to misinform, they're using carbon electrodes. Why do I like carbon electrodes? Carbon electrodes are much lower cost than gold and platinum. At ZP, we do use gold electrodes. I just did a whole, 10-minute talk on molecular assays. And, there I was often thinking about gold electrodes. But if you can ever use carbon, and you can use them for molecular assays as well, but if you've ever got a choice in life, choose carbon electrodes. Carbon doesn't have the kind of competition for it that gold and platinum do. Platinum's a good catalyst. It has a sort of luxury market as well. Gold is a good catalyst. It's inert. It's used in electronics. It has a luxury market. Not so many people care about carbon. So carbon is a good substrate. And then they do the analysis. So then they do the signal. Let's say by looking at the voltammetry, probably looking at the reduction of those silver ions to silver. And no criticism of the paper. They've got some error bars in here, and those error bars are possibly in part coming from the screen printed electrodes. So now at ZP, we're very keen on somebody just asked me, is this kind of paper translatable? And the paper is very translatable onto the ZP platform. Why would you even want to do that? Well, because actually you can then get those kind of assays out of that lab on into the market. What we have is a workflow where we have a potentiostat, and we have screen printed electrodes. They will have been previously functionalized with the zeolite silver clusters. You can bring the sample on, let's say that glucose sample. We can run assays. In fact, I'm showing here Chile, but I just want to show you very quickly. In their particular case, they're probably doing something like square wave voltammetry. So they could have done square wave voltammetry, and then we can look at all the settings, and then we could start the measurement. So I'm going to cancel that because I got no sample on there. But you can then get sophisticated. So at ZP we have a glucose sensor. So in fact, we're able to not just people are not just able to just do scientific experiments. They can actually use our data pipe and actually start making assay specific QR codes. So what we're trying to create is the idea that you've done all your method development, you've got your calibration curve. If you put your calibration factors in our cloud, you can then turn your raw signal into something meaningful: pH, nitrate, glucose, potassium. You're not limited by this list. Testosterone is also in here as well. You're not limited by this list. You can create your own QR codes. So that said, we have a very elegant potentiostat, really quite a nice device that's driven by QR codes. The sample goes on the sensor. The app runs the meter. The meter gives the data back to the app, and the raw signal, it could be square wave voltammetry, for example, is sent to a cloud system called Julie, which I'll do a demonstration on shortly. And we have things like pre-processing data. So ZP, we really have become really a group of data scientists, that electrochemistry, electrochemical sensors, electrochemical biosensors, wearable biosensors, these are all conduits of data to the cloud, where we've got really good at processing data. So we'll do some pre-processing, we'll do some processing, and we'll actually send a concentration back to the phone. And I should really do a demonstration on that now. So in fact, what I'm going to do really quick is go to this screen. So hey, welcome to the Sense It All Potentiostat. Let's take a biosensor. Let's put it into the device. Let's do a real world demonstration. Okay, what should we do? Let's scan a QR code, which I will do. Right, now this is in connection with this. Hey, let's take a real sample. Here's a real sample. This is why you should love electrochemistry. Look at this dirty, horrible, bitty sample, which I will now run. So I will take a sample of that. Let me just grab a pipette tip and off we go. Flick. The other thing about electrochemistry as well, actually, what I really like is it does not require a lot of sample. I'm putting 50 microliters onto this. We could put some effort in and put some microfluidics on this and actually reduce that quite significantly. Let me just go to this. Let me just put in the words something like Stefano, so I can find this in a short while. Go continue. I'll go start, and off it goes. So I know that something's working because I'm getting a sort of stream, and now I'm not expecting the end user of this particular this particular application to actually interpret that data. It wouldn't be particularly fair on them. But what I'm going to do is I'm just going to share my screen, but I'm just going to just go to a system called Julie. So I've got a result here. So I've done an electrochemical experiment, but I've given them a result. So we can take papers like the one I'm showing, run their square wave voltammetry, put it through a data pipe, and actually give a result. But how did I do that? So what I've done is I've got a system called Julie. This is integrated with the app, and I'm going to share my screen. Boom, this is Julie. Let me just go to something called a cluster, which is my demo cluster. Let me just go into here. 1, 2, 3, 4, 5. And I find my device, SIA, Sense It All. There's Stefano. So this is what I just ran just now. Here's my, in this particular case, my cyclic voltammetry. Here's the result. This is the result that we showed on the phone. So, I know that will be too small for you. But there's basically a result on my phone, and there's a result in the cloud, and they say the same thing. But this is the bit that I really want people to understand, that what we're doing is we're saying, okay, on scan 2, I want you to pre-process that data. I want you to do a low-pass filter on that data. I want you to flip the data around the y-axis. I want you to crop that data. I want you to go and find me the peak height centered on 250 millivolts on the reverse scan, and I want you to fit it to this formula. Please understand that scientific papers like the one from Stefano here, they do this work. They've got a method file and they have a calibration curve. So that calibration curve has an equation associated with it. And if they put that into this cloud, it will mean that when the data goes up, the data comes up. In this particular case, we analyzed the second scan. We pre-processed it, and then we told it, go and find a peak in this particular potential range. Tell me what the height is, put it through the formula, and you know what? Deliver me the actual concentration. And it's this last step that's really holding back research, because all the potentiostats in the world, apart from this one, are designed just to gather scientific data. This one has gathered perfectly good scientific data, really nice. But what it's done is it's just gone the final step and actually processed it. And if you look back then in our data pipe technology up here, I mean, look at all the formulas that you can fit to: linear, quadratic, square root, inverse square, semilog, semilog y, double log, exponential, Michaelis-Menten. We've got so much functionality built on this, and this is why at ZP now we're kind of thinking ourselves, we really are data scientists, and anyone doing electrochemical sensor development, you really are just a data scientist. You're a conduit for really useful chemical and biological data, but you're a data scientist, and the Julie platform really does then process electrochemical data through a data pipe and turn it into, in this particular case, 1493 micromolar. So now I will go back to that. So why did I do that? So at ZP, we think there's a lot of papers being published in the literature, especially in the world of electrochemical assays. We are very keen for people to actually use our potentiostats and our screen printed electrodes. Why? Because they're a real conduit for actually translating that exact kind of research into something that you can actually roll out and put into, let's say, the real world. And that's how we have impact. Otherwise, the research will just remain within the lab. Just some work that we were doing this week, in fact. It's bad to say this, but I'm not, in some applications, graphene has a real, let's say, killer. But in the world of electrochemical biosensors, I actually think, if we look at one of our graphite electrodes versus one of our graphene electrodes, my purist colleagues would say, oh yeah, well look at that. You've got more signal and you've got a less peak-to-peak separation. So they would look at the graphene one, which is in blue. They would like the increase in peak height. They would also like the fact that the two peaks are kind of closer, so it's kind of showing a more Nernstein behavior. But for me, it's all about reproducibility. So at ZP, we think that often people are actually assessing screen printed electrodes or electrodes for biosensors on the wrong parameter. They will look at sort of classic electrochemistry KPIs, key performance indicators, like is your signal proportional to the square root of scan rate? That's the simplest box in the world to tick. Most of the time, you can have a really bad electrode, but the signal will still be proportional to the square root of scan rate, because it's actually the molecule in solution that's giving you that relationship. It's not so much the electrode is so important in that case. Probably what is important is if you were looking at peak-to-peak separation. So at ZP, if we're making a screen printed electrode and we're doing a low scan rate on something like ferricyanide, we may end up with a peak-to-peak separation of something like 67.5 millivolts. Ideal is 59 millivolts, but it's the wrong parameters that, in my opinion, the parameter that you should really care about when it comes to electrodes, especially if you've kind of got the mindset of ZP, which is how do we translate all of this research into products, is actually reproducibility. I said it earlier on, if you watch a demonstration from ZP, in fact I just did a demonstration, when did you see me do a calibration there? No calibration. No calibration, because actually we have very reproducible electrodes. No calibration means simpler assays. Simpler assays mean easy to commercialize, and if it's easy to commercialize, it's easy to have impact. So at ZP, we really do focus on, we may do very classical electrochemistry in order to test our manufacturing quality, but we're really testing our screen printed electrodes before they ever leave the factory to make sure that our relative standard deviation on something like peak height is single digit. In this particular case, our repeatability, or RSD, is relative standard deviation, that is for peak height, is like 6% on one of the sheets and 5% on another sheet and 6% on another sheet and 6%. And I was recently looking at some gold electrodes where actually the relative standard deviation was actually 3%. And it's this irreproducibility, whether the electrodes are produced in-house or whether you buy them from third parties, which is often holding research back. They're just buying electrodes that are basically out of spec and not using the data in the actual papers, so they lose both the electrode and the time and effort of making assays on those sensors. Or they're then starting to try to bring in like calibration on the sensor in the actual application, and trying to add complexity like calibration in an assay that's meant to be low cost, easy to use, is not a good strategy, and it is really just coming about because of the irreproducibility of the screen printed electrode. So we do make a big effort for that. So at ZP, you will see that many of our assays that we sort of talk about online don't have calibration. I'm going to do a demonstration in a bit, so hang on for that. But I'm going to do it when I talk about urine detection in glucose. But why do we have this philosophy? And if you have a look at my LinkedIn profile, you'll see that the first job I ever had was actually making glucose strips. So I have a slightly different background to many of my colleagues. My first job outside of after PhD was actually making biosensors. And when I was in the world of biosensors, the whole market was changing to calibration free. So of course at ZP we have the same philosophy. We want to be calibration free. We don't always achieve it, okay? But when we can, it's at least a philosophy that drives us. It's the first thing that's kind of on mind with us with that ZP, and I understand that manufacturing reproducibility of things like screen printed electrodes is actually what drives calibration free. So the paper from Stefano is actually quite straightforward on our platform to actually commercialize it. Commercializing is too strong. So there may not actually be a market for that particular assay, but at least to get those kind of assays out of the lab and into the hands of real users. I mentioned Geosmin. Geosmin's a tricky molecule, and we do get requests about Geosmin. The nice thing about if you watch ZP webinars is we don't just talk about science, the science of biosensors. We actually talk about applications as well. So this is a molecule that is it's given out by bacteria. So people have these recirculating aquatic systems where they're growing farms. So it's basically associated with fish farming. Fish farming, generally, that's done on land. And you can get bacteria into these systems. The bacteria can give out this geosmin. the geosmin can build up in the fish, and then the fish will have a slightly earthy taste, which will put the consumer off. It's a hard molecule to electrochemically detect. So, if I was to work on an assay like this, of course, I would use my Sensi-All platform, because we've got most of the, we've got the screen-printed electrodes in place, we've got the instrument itself in place, we've got a very elegant app system in place with QR codes and the cloud system in place. So that would be my, obviously, biased go-to market kind of strategy if I was doing a Geosmin assay. But the thing about Geosmin is it's a part per trillion molecule. So part per trillion is really a hard thing to do. But if you're interested in Geosmin, then I would start reading around the PFAS papers. Polyfluorinate fluoroalkyl substances, PFAS, polyfluoroalkyl substances. This is a problem that's blowing up at the moment because I don't want to say which. They call them forever chemicals. There was a film made, I think, with Mark Ruffalo called Black Water, where they were talking about these PFAS, these PFAS molecules. They're toxic. They're in the environment. They're toxic at very low levels, and so there's a lot of impetus, especially in the US now, to spot these PFAS molecules. The only reason I bring up PFAS is because it's also on the face of it, quite a hard molecule to detect, and it's also in the parts per trillion. So when I think about Geosmin now, and if you're interested in Geosmin, look at the PFAS literature for a kind of clues to maybe how to solve this problem. And I'd hope that you would consider using the ZP screen-printed electrodes because they're so reproducible, which would be really important for this kind of application, and also our Sensi-All potentiostat as well. Again, because we actually have this instrument, you can put the sample on there, you can develop an assay for it. We can send I suspect you'll end up using something like square wave voltammetry in this kind of assay. We could process that in the cloud and actually then send back a sort of a Geosmin concentration back to the phone, but it will be in parts per trillion. So it's a limit detection. That's the really hard part with this. Now at ZP, we do a lot of materials around biosensors. One of them is silver plating. So we've got a client who's been doing some silver plating, but it's very dull. That's not a nice shiny looking surface. But I suspect that what they're doing is too high a deposition rate. So they've basically got the current density. These are the current density just means current per surface area. The current density is too high. So rather than getting a nice kind of smooth deposition of silver, or electroplating of silver rather, they're getting a rough surface, and that rough surface then appears dark. So simply decrease the current density by a factor of 10, for example, and then you'll probably get a shiny surface. And then you can kind of start optimizing that current density so that you have a fairly rapid rate of deposition, but you don't get the kind of you don't get it so fast that you actually get a rough surface, and a rough surface will appear dark. Just out of interest, even if you get a rough surface in biosensing, that might be good enough to work as a reference electrode for you anyway. You don't necessarily need the aesthetics of a shiny surface, but if you do want the aesthetics of a shiny surface, then decrease the current density by a factor of 10 and see if that improves the situation. What's wrong with potentiostats? Well, I don't think there's anything wrong with potentiostats, but it's a kind of question that's kind of been posed, and I'll go through it because obviously at ZP we do have a brand new type of potentiostat. This is not, it's even got these nice LEDs on the front that kind of really guide the user experience. In fact, I can sort of, so we've got a very elegant one, a potentiostat. What makes it slightly elegant as well is actually no cabling involved in this potentiostat. So many potentiostats, in fact, I've got some PhD students running at the moment where they've been misconnecting the counter electrode and the working electrode, and so doing voltammetry. No criticism of them, and I'm very kind about it, but it's just something I would have done myself. So potentiostats have problems, and one of them is sometimes complexity. So let's have a look at what the problems people think are. There's a high cost of advanced potentiostats. In the world of biosensor development and biosensor, let's say, manufacturing, you do not need complex potentiostats. In fact, complexity in your assays is going to make it harder to translate them into assays. So we don't need complexity. Complexity often means high cost. These particular potentiostats I don't think are actually super high cost. They're actually super reasonably priced, much lower cost than definitely competitive with what's on the market, and a lot more functional and a lot more easy to actually translate into products. And then they also sort of say, there's a complexity of operation and also one of data interpretation. Now, the nice thing about ZP as a potentiostat developer and manufacturer is, of course, if you're using our screen printed electrodes and our potentiostats, then we can support. Look at this. This webinar has been going on for a good, I'm not even sure, 56 minutes. So this is the amount of support that we actually give to, let's say, our technologies and our knowledge. So you get a natural support through the webinar series. Now, it's not hard to use. Let me just bring that point up a little bit here. Let's choose which technique we're going to do. We'll do cyclic voltammetry. So I'll scan the wrong QR code. Let's scan the wrong QR code again. Cyclic voltammetry, go continue, and simply got start potential, turn voltage. So sort of where do you start, where do you go to, what's the scan rate, and how many repeats, and what's the current range that you want to use. And of course, because we have these webinars, if people get stuck, then you can expect to get a video response like this within the week, let's say. So I realized that, and then the interpretation of data as well. If you watch ZP webinars, you'll actually find out that we're really good at supporting and interpreting data. In fact, people send me data, I make video responses on it, I anonymize it. So ZP potentiostats, they don't require the same level of expertise because ZP has such a good policy on actually supporting these kind of things. I don't think there is a limit of accessibility to these kind of instruments. In fact, I think what makes these instruments quite unique, in fact, is that non-electrochemists are actually able to use them and students are able to use them. There is no continuous calibration and maintenance needed. I mean, this is a solid state device. There's nothing to really go wrong with this kind of device. Keep it simple, keep it solid state, and then you've got quite a robust little instrument. We've even taken really great care over the way that, if you look in there, these are little pins. Many of these potentiostats where you're trying to slot in something at the front of the potentiostat. Look at this, it just clicks up. That's really elegant. No cabling, no making mistakes on the cabling, no damaging a connector, no ingression of liquid into the connector. Really well thought through by, basically we have a very strong product design team. We don't need to do regular calibration. I don't think this is actually, in fact, you saw me do a demonstration earlier on. This is not time consuming. And they say here a rapid pace of technology change. The technology, people are adding new features, but I think they're actually thinking of this in the wrong way. What is the point of electrochemical or analytical electrochemistry? The point for me is actually to get it out of the lab. So people are developing more and more better lab-centric instruments, and ZP is building a portal to get data out of the lab and into the cloud. So we're just taking a completely different philosophy to the let's say the problem. Question number 7. Okay, so question number 7. Somebody was asking about Aptamer sensors last week, and they were kind to contact me and said it was helpful. I'm glad. They are not using ZP screen printed electrodes, so we do run these webinars in a way that we will support people. But this is a kind of classic, actually, that they've used one vendor. It wasn't very good. They have found a better vendor, so that's fair enough. So, it does show you already that my comments about not all vendors of screen printed electrodes are equivalent. And what makes ZP very different is when I'm answering this question about Aptamers and gold electrodes, we've done at least, we're doing a product development with a client at the moment. And every time we do an experiment for the client, we actually do 80 experiments within that experiment. So we will try to answer a question about an assay. How many sensors do we run to answer one question? Like 80 screen printed electrodes. So we're just doing this at scale. That's not, most people would do 80 in order to develop an assay. They wouldn't do 80 sensors just to answer one question. And we use our own gold screen printed electrodes there. I did mention to them that when we're doing this kind of work, we're often using self-assembled monolayers. We may have an aptamer and a spacer molecule called MCH, for example. And we would actually have them in solution at the same time and drop cast them at the same time. and then put them in something like the fridge or overnight, sort of 5 degrees C at 12 hours is what we would do. And yeah, so the quick answer is that we would actually be doing the deposition of MCH and the Aptamer at the same time and putting that in the fridge at 5 degrees C for 12 hours to let the kind of molecules arrange themselves. I mean, when I first started doing this work, I started doing this kind of work on a commercial product in California 15 years ago. And that's when I realized, obviously, this incubation was important. And I must admit, it feels a bit like, the fact that we do it at 5 degrees Celsius, it's just a trick and a tip that I've picked up over the years, but that would be my recommendation. And I appreciate the feedback as well. I also like the fact that the guy was kind of criticizing himself, saying, well, what I'm doing is not that innovative. And I said to him, and he responded on it. Not many people are doing impedance spectroscopy in the commercial setting. So every year there are 25,000 electrochemical biosensor papers produced, and they're not translating into real products. So when we think that it's all been done before, it has all been done in academia, but it's not translating. Why is it not translating? The potentiostats are wrong, the gold electrodes are not reproducible, and of course the hardest thing is the business case. What am I is what I'm doing actually of commercial interest as well? So as I say, in this particular case, they're not using our scooped electrodes. I'd love it if they were. They're not using our potentiostats, but I just want to also demonstrate that at ZP, it's not, we will support the community in a sort of wider context as well. Somebody here is interested in making a CGM, a continuous glucose monitor. They're thinking of making a platinum rod, a silver rod will be their reference electrode, glucose oxidase powder, a glucose solution to test it, and then like using PBS, and then an ammeter, to measure the current. I just feel like this is kind of, this is too R&D. I mean, if you want a CGM sensor, continuous glucose monitor sensor, in order to kind of move yourself forward, especially in a commercial setting, building glucose sensors from the ground up is not teaching you anything. I mean, the first glucose sensor was made in about 1957. The first electrochemical glucose sensor was made in 1957. Today we're in 2024. It's wrong to go and rebuild glucose sensors from the scratch like this. If you want a CGM sensor, you can find a CGM sensor on the ZP website. Buy it, try it, learn all your lessons from it. So you can buy CGM, continuous glucose monitoring sensors, for doing lab proof of principles. You can buy test solutions from ZP. You can buy rinse solutions from ZP, so you can reuse the electrodes. You can buy the electronics from ZP, especially OEM solutions. So just kind of saying, lots of, if you want to get into CGM, don't go all the way back to ground zero, which is let's immobilize some glucose oxidase on a platinum electrode. You can even buy those kind of solutions from ZP. If you're a commercial company, you need to go forward very quickly and not go backwards. Let's say essentially what you tried to do is going back to 1957, and today's 2024. So this is a question that's has come in. So somebody's interested in doing sweat analysis. So just FYI, theoretically our cortisol sensor and our testosterone sensor are usable in sweat, but we have not done it. And when it's a sort of group that's let's say is short on time and potentially short on money, I can't recommend you get into the cortisol and the testosterone sensor. The cortisol sensor is not something that we will sell online anyway. We've got very large customers using the cortisol sensor. They're very well funded. We actually do have the testosterone sensor available on one of our platforms. I'm just going to go here. So here's my Sensei All platform. We do have testosterone sensors that look surprisingly like this. And we actually have it on the app as well. So just FYI, testosterone sensors and their release to beta users who are then starting to use them in measuring testosterone in saliva. And I know you're interested in sweat, but in saliva, that is going on. But when groups are kind of university based and have a very limited budget and a very limited time, I have to sort of strongly make my recommendation. So my recommendation is focusing on potassium. So these electrodes from ZP, biosensors don't really care what the matrix is. They don't care if it's blood, urine, sweat, saliva, tear fluid. They really don't care. It is important because it affects the calibration routine or even the analysis routine. But the sensors themselves don't care. So don't get this thing that actually the sensors care. So the potassium sensor we have, for example, was originally developed for measuring in blood. Its most applications actually for been measuring potassium in sweat. And they're also interested in the schematics. So I will give you the schematics. You can freeze the video here and just get a schematic. But I do appreciate if people are customers, then we can give them materials. But of course, if they're not customers and just trying to fact find, that makes it a little bit harder to support. But just for politeness, here's the schematic. You can sort of pause the video, let's say. I would recommend reading the background to this and understanding the limited budget and probably the limited time. And you want to, you can have a roadmap where your roadmap is, I want to do cortisol, I want to do testosterone, I want to do potassium. Well, the first thing you have to do is one of them. So my recommendation is, we've got potassium sensors on the ZP website. We've got calibration solutions for testing those kind of potassium sensors on the website. We've got an electronic set for driving those potassium sensors on the ZP website. We've got a sweat patch. Now, so you can basically immobilize these sensors theoretically onto the skin. And we've also got a rinse solution, so you can sort of rinse the potassium off and store the sensor away for later use. So that is a fairly good kit for allowing somebody to do a TRL level 3, technology readiness level 3 kind of test of a potassium sensor. The cortisol sensor, unfortunately, from ZP, we will not release that unless it's to really well-funded clients. The testosterone sensor has never been run in sweat. If people are interested in measuring testosterone in saliva and they're a startup company and have the kind of funds to really engage, then that is a kind of technology you can get from us. If you're kind of more university-based, more kind of student team-based, then I would actually just focusing on the potassium sensor, and these links will give you a useful technology stack that you could probably do a TRL3 kind of piece of work with. If people are well-funded, by the way, you're welcome. If you're well-funded and you can afford, let's say, the time, we are bringing people to not bringing, they're paying their airfares, they're paying for the engineering time, and they're coming to Norway and actually doing sweat analysis type programs with us at ZP. But unfortunately it does, let's just talk about numbers for a second. See this CGM sensor from Abbott. I would easily estimate that Abbott has spent over $1 billion easily developing, commercializing this technology. So cortisol, testosterone, and potassium. If you're trying to do it at a medical level, these are $1 billion programs. I think Dexcom, who also make a CGM, a continuous glucose monitor, spent $500 million getting to market. BioLink in California. BioLink have a microneedle watch. This is not theirs. This is ZP's microneedle watch. This particular microneedle watch, which will do continuous monitoring, akin to sweat, but it's using microneedles. $20 million has gone into this so far. BioLink, who have I don't want to say similar, but they have a technology that kind of has some overlap with that, have spent in the last 4 years $158 million. So people really do have to understand that it's a large engineering lift to do anything continuous, and people probably have to engage even just with consulting and advising with ZPs, because we'd have to road mapping this stuff out. But these are not low cost efforts. So when I say to you do potassium, it's because I can think that with the budget and the time that you have available, it's the one that will give you the most probability, as long as you have the engineering and scientific skills, of success. I hope that is useful. So somebody wants to do CGM detection, continuous glucose monitoring on microneedles. So again, we do have some kits that will help them. We do some microneedle kits online. You will have to do a couple of functionalization steps. You will have to put the enzyme formulation down. So ZP does have a glucose oxidase enzyme formulation. You'll also have to put a barrier layer down as well. I know you've come to our workshops, but just FYI, I've done a lot of videos online about the use of barrier layers in glucose sensors in order to get the kind of linearity. So at ZP, we do have construction kits. So when I say construction kits, we have microneedles available. We have enzyme formulation specifically for glucose available. And we have barrier layers also available as well. Now, what I would say is it's quite expensive, those microneedles. I would say practice on screen printed electrodes. So practice on our platinum hyper-value screen printed electrodes, because then you can afford to make mistakes. If you can get it working on the screen printed electrode, then you're ready to translate onto the microneedles. Otherwise, you're doing your kind of development or your functionalization on the microneedle, and that could be a very expensive platform if you make mistakes on it. So I'd actually practice on the screen printed electrode. So I'll put a link. Any links that appear in this video will also be put underneath the video as well once I've gone finished with this. You'll need some electronics, so the single-purpose biosensor circuit, and you will need some test solutions and a rinse solution. It's important to rinse glucose sensors. After you've used them, you want to get the glucose off the sensor so that you can then store it. The reason being is if you leave the glucose on there, it keeps on reacting with the enzyme and produce hydroperoxide, and it will shorten the lifetime of that sensor. Any links that I've used in this video, I will also put underneath as well. Somebody's got a flow cell from Zimmer and Peacock. They're thinking about using it with our glucose sensor. So they've got one of these kind of kits. I've just been helping them understand how to put the sensor into the flow cell, how to kind of line it up. So you can see there's electrodes. It's all quite straightforward. And then they've got one of these little kits where you can sort of put the electrode in there. In this particular case, they're actually not flowing. It's a pipetting one. But we do have some quite interesting accessories at ZP for handling our sensors. So if you've got any questions around what kind of rigs and jigs do you have for helping me handle sensors at ZP, we do have quite a lot of technology around there. Now the last one, I think this is the last one but one. Somebody's got a single-purpose biosensor circuit. This single-purpose biosensor circuit has been linked to earlier on in the video. They want to use it for cyclovoltammetry. At this moment, this single-purpose biosensor circuit is not a it's not a potentiostat. We do have potentiostats. Bang, here's the Sensi All potentiostat from ZP. I think it's one of the easiest, best for translation of academic research into products, potentiostats on the market. That's a potentiostat. That will do cyclovoltammetry. Yeah, there we go. That will do cyclovoltammetry, no sweat. But what they've bought is not a potentiostat. They've in fact bought it for measuring with our calcium sensor. So it's been programmed to work with the calcium sensor. It's not a potentiostat. Just FYI, wearable potentiostats from ZP will be coming out probably in Q1 2025. But what you have is for measuring calcium sensors. It's not a potentiostat, so it can't do cyclovoltammetry. Right. Okay. So last question. And it's not funny, but sometimes questions can seem very simple, but the answers are not simple. So somebody wants to measure glucose in urine, and they would like 80%, let's say, accuracy on that. So let me use this as an illustration. When I say illustration, let me use this as an illustration. So let me take a glucose strip. Let me put it into the glucose meter. Right. Let me take a sample. Right. I was just being a bit, let me get a bit of blood. Right. So that's just doing a countdown now. By the way, that 85% accuracy is actually the same accuracy that you get with a glucose meter like this. So my blood glucose at the moment is 104 mg per dl. I'm just going to check that accuracy. I mean, this will check the precision actually. This is not checking accuracy. This is just checking precision. So I'm just going to do another reading just real quick. 104 mg per dl. 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 104 because that 85% accuracy you're actually asking for is the same as what a glucose meter has today. Now these glucose meters for blood, they've been around easily 40 years. So there's a lot of engineering gone into that kind of technology, and they've achieved 85% accuracy. So you've got to understand. Sorry, I'm being a bit scaredy, let's say. Just going to do this again. Right. Just interesting to see. I think the last one was 104, so it'd be interesting to see what this one says, because obviously the time gap between those two is quite short. So yeah, we are. I've got 100. So rather crudely, I've got two readings, one at 104, one at 100. It's crudely about a 4% difference. You know, they're pretty accurate, but in fact the standard, the ISO standard for this says that they have to kind of be accurate with a sort of error of 15%. So your accuracy of 85% means an error of 15%. So you're asking the same question. Now that's 40-year-old technology. You know, they didn't get to that overnight. In fact, the first technologies that they did, putting blood everywhere now, the first technologies that they did have, they used to even do a point of calibration there and then they would have QR codes like this, which would then calibrate the meter. They're calibration free these days. All right, now why am I saying all of this? Let's go back to the question itself. Okay, so somebody wants a very accurate urine glucose sensor, and I've just done you a demonstration where I have shown you accuracy on a commercially available blood glucose meter, but I've also given you a bit of a background on that's 40 years, and they went through a whole roadmap of technology. So first of all, they would calibrate them there and then they went calibration per batch, so there'll be a QR code associated with each batch, let's say, and they in fact even had little inserts to calibrate the meter based on the sensors, but they would have batch to batch variability, and these days they're all calibration free. Great. That's a journey, and that journey has been going on for about 40 odd years, and it's easy to say that billions have gone into making them calibration free like that today. And I did you a quick demonstration. Now let's look at blood. So my blood is quite pH controlled. You know, my blood will have a pH of about 7.2, and if it's not 7.2, I'm in deep trouble. So the body is really good at holding blood at pH, let's say 7.2. And also my electrolyte is controlled. What I mean by that is my sodium levels, for example, in my blood are about 135 millimolar. You know, so a lot of parameters around my blood are really well controlled, and if they're not, I'm dead. Urine is got a pH range of 4.6 to 8. So urine, these are orders of magnitude difference in terms of proton concentration. And then the electrolyte is also changing. It can go from 150 to 300 millimolar. Whereas I said with blood, it's actually quite fixed. The reason I bring this up is because you're asking for an accuracy of 85%, but you've actually got a lot of science to really think through, because you are not dealing with a standard sample, you're dealing with urine. So you really have to think about the science and engineering of actually standardizing that sample before you do the test. Now I will list out a bunch of technologies that you can get from ZP to help you, but let's be very clear. Our technology will bring you to our technology will actually bring you all the way to market, but that's only with really well-funded clients. If you are, I'll give you a low-cost, let's say, way of getting some low-cost technology, but you will need a glucose generation 1 sensor. This will just get you to technology readiness level number 3. Technology readiness level number 3 is a proof of principle in a lab environment that what you have is fundamentally working. It's not and clinically I can get an 85% accuracy in urine, because urine itself is going to give you more noise in your signal than the actual glucose sensors themselves. But to get you going, here's some glucose sensors, here's some test solutions, here's some rinse solutions so that you can actually rinse the electrode down after having urine on it, or rinse it down after having some glucose test solutions on it. And here, here's some electronics to drive that glucose sensor. And yeah, there's that's there. And also there's a potentiostat. If you want to use our sensor or potentiostat, you can also use that. But I have a feeling that you're more a product development person, so you may find the single purpose potentiostat more conducive, let's say, to what you actually need. So when people ask questions like, oh, I want to do glucose in urine and I want an accuracy of 85%, of course, when ZP answers that question, we're answering it from, I made my first commercial glucose strips in probably 2000, so this is now 2024, so 24 years, approximately that is. 85% accuracy, sure, glucose strips are 85% accurate, but that's after 40 years. To get 85% accuracy today on urine, I don't think anyone's doing it. You probably need calibration routines. You probably need a system approach, not just think that the sensor itself is intrinsically going to do that. And I just listed out at least 2 parameters that are quite out of your control when it comes to urine: pH and electrolyte concentration. Biosensors, unlike other sensors, the sensor is in intimate contact with the sample. If it's a temperature sensor, there's a temperature sensitive element and it's sitting behind some material, so it's quite shielded from the sample. With biosensors, it's not the case. We're actually in the sample. So sample, in your particular case, will be the biggest source of inaccuracy because of its irreproducibility than the actual sensors itself. Can people do the measurement of glucose in urine? Of course you can. You can get glucose strips. But just don't think that, one of our glucose sensors, you can just put it in urine and you'll get accuracy. No, if the pH is 4.8 or the pH is 8, that itself is a source of variability and a difference. And you get a difference. The glucose is otherwise the same. The sensor will respond differently because of those different pHs. Question number 1. All right. So let's have a look at time. 1 hour, 21 minutes. So let's go quick. All right. Question number 1, configuration of molecular assays. There are at least 4 assays I listed there. There were 4 assays. 3 of them were simple. 1 of them was more complex. What's the philosophy at ZP? Go for simple. It's easier to commercialize. Can we take something like these silver clusters in zeolite to commercialize that kind of thing? Yes. Use the Sensor platform. It's what's holding back so much scientific research is reproducibility of the screen printed electrodes, and the potentiostats are R&D potentiostats. They're not designed to actually commercialize the R&D. This is both an R&D potentiostat. It has a cloud built into it, and therefore you can actually turn your raw signal into concentration. So we do like, or we want more and more academics to adopt our technology so they can actually at least make their science, let's say, more impactful. Graphite versus graphene. Graphene, I'm sure, is a great material. It doesn't really add a lot of value in biosensors. You can buy graphene screen printed graphene electrodes from ZP. You will find them online. It's the reproducibility and cost that's more important. So I actually just say use our graphite or carbon electrodes. Geosmin testing. Geosmin's going to be tough. It's the parts per trillion that's tough. But that makes it no more tougher than PFAS. And so if you're interested in doing Geosmin, I think that the hint to how to do this is probably in the PFAS literature. Silver electroplating. If you're electroplating silver and it's all rough, reduce the current by 10. And by 10x, and then try again, and you'll probably find that it does work right. There's nothing wrong with potentiostats. They are often complicated. They're often too R&D focused, and with ZP, this is not a hard potentiostat to use. It's elegant. It can be used by non-experts. There's a lot less risk on the cabling. We've got easy ways of connecting, easy ways of cleaning, easy way of mounting the screen printed electrodes, easy ways of driving it off the app. And by the way, when it's run the assay, the data goes straight to the cloud. So I hope that is super useful for you. Aptamer sensors. Yeah, I didn't add so much value this week, but I'm just trying to confirm some of your questions. I'd be delighted if you did translate onto our gold screen printed electrodes. I appreciate you're not at the moment, but you can see that we do try to help people despite that. With the CGM, if you're a commercial company interested in doing CGMs, you probably should engage with ZP in a deep and meaningful manner. It's no point in building from scratch again, because that has been done, and that was done in 1957. So I think, 1957, we're talking 43 years to 2000 plus another 24. So we're talking 67 years ago, so closer to a century. Hormonal longitudinal tracking. There are lots of people trying to do continuous testosterone, cortisol testing in sweat. Our cortisol sensor is not available unless it's to a really well-funded clients. And we are actually launching, or we are shipping testosterone sensors, but admittedly, they're most of those clients are using it in saliva. If you do want to get a first step, and it's a roadmap, first step on the way to doing continuous monitoring in sweat, please use our potassium technology. The glucose microneedles, I've given you all the links to the microneedles, the materials, the electronics, the wash solutions, and practice on platinum electrodes first. Screen printed holder, and then the biosensor circuit is a circuit for doing biosensors. It's not actually a potentiostat. And then the glucose in urine is a fun question at the end there, just to kind of put some context about, you know, the journey that it takes to make accurate sensors. You know, let's look at the glucose strip, and then let's just think about how blood is actually quite a repeatable matrix compared to urine, and I gave you some rationale for that. So if you've got any questions on ZP, please don't hesitate to reach out to us. Okay, so that's 1 hour 25 minutes. I think you've heard enough of me. I need to drink some water, but I want you to have a good weekend. Okay, thanks very much.